Really,
thank
really,
you.
really helpful.
Thank
Really
you.
helpful there.
Appreciate that.
So while he's drawing, what is Carmella?
Carmella is it predates Stoker's Dracula by about 30 years,
Oh, really?
but it is vampire. And it's a Irish author. He's an Irish author, and it's about 100 pages or so. It's more of a short. It's more of a novella. It's fun to read because it predated Stoker, and I was like, well, sure, I'll try it.
So it's gotta be better than Dracula.
You're reading along.
So I would have drawn it better,
Excellent.
but this is it for right now.
Casey, did you know all this from memory?
No, he had sticky notes.
Yeah,
Oh,
I have a note.
Okay.
Okay. I probably could have, but I just
Here, let me move this. Do you need the podium?
Sure. So exciting. Okay, so that's my picture. My project for this year was basically to try and build a liquid oxygen based model rocket. I say model, I planned it on being about this tall, which it probably would have been if I had money to build it, but I don't. So unfortunately, it's all just ideas on how the rocket would have worked. So first off, I probably have to go into an explanation as to why or what liquid fuel is, because it's much different than solid fuel, which is what practically every model rocket runs off of. The differences are really self-explanatory in the names. Solid fuel is literally a solid fuel, and liquid fuel is liquid. Solid fuel is a lot easier to get, it's safer, and in terms of model rockets, especially when you're making like a small one just to see it go up and go fast, is a lot better because solid fuel essentially has actually a much bigger bang than liquid fuel does. Liquid fuel has a much smaller bang, but what it does have is a much bigger bang per buck, essentially, and that bang per buck is called a specific impulse. Specific impulse is essentially how much thrust are you getting out per unit of fuel used. So when you're using solid fuel, for example, on a smaller rocket, you'll have a much bigger thrust at the very beginning and it'll go really fast, but you'll run out of fuel pretty quickly. And in terms of practical use and actual space travel, it has been used before. There are some examples of NASA in which they strap massive solid fuel boosters onto the sides of their main engine, which is liquid fuel based, just because the liquid fuel, because it has a smaller thrust to begin with, it can't lift itself off the ground. It needs that bigger bang at the beginning to start getting it off the ground. Liquid fuel, and why I wanted to do it, is a lot easier. For one, you can turn it on and off. And that might not sound like a big deal, but it's a pretty big deal. You can turn off liquid fuel mid-flight and then turn it back on later whenever you need it. Solid fuel, once you ignite that solid fuel, it will keep burning until it runs out of fuel or crashes into the ground and explodes. And solid fuel, liquid fuel, another advantage is that although it doesn't have as much of a bang, you will actually get more delta V, which is delta velocity, change in velocity, out of liquid fuel. It'll take longer to get that change in velocity, that extra boost, but it is there. So if you do have a liquid fuel based rocket, even with the same amount of fuel relative to each other, you'll get higher with a liquid fuel rocket. You just might not be going as fast initially, which can raise some problems with, getting off the launch pad or, lifting heavier cargo. But the reason for that long-term gain is why a lot of places like NASA and SpaceX prioritize liquid fuel over their solid fuel. But into basically what I've been doing all year is a lot of research into the practicality of trying to make it small scale. And the answer is it's not. It's not practical at all. Very difficult, mostly because in order to make liquid fuel, you need two ingredients. You need the fuel, in which my case I would have chosen RP1, which is a rocket fuel, and you need an oxidizer. An oxidizer, you know, flames, they require like the three components and all, and you know, one of them is oxygen. Oxygen essentially makes a flame much bigger. And in a normal fire, it just lets it live. But if you were to take a normal fire and then douse it with liquid oxygen, it would just go up in huge flames. It would make it a huge fire. And that's basically what you're doing with a liquid oxygen-based engine. You're taking a very ignitable fluid and you're putting it in a very tight chamber, blowing it up, and then just shooting as much liquid oxygen into it as you can to make that flame as big as possible, to make it as powerful as possible. The downside to that is liquid oxygen is actually counterintuitively extraordinarily cold, like negative 270 degrees Fahrenheit cold. So whenever you're trying to do literally anything with it at all, it just doesn't turn out. If you put it in like normal metals, it cracks. You know, there's a lot of critical points in metal that are much higher than what liquid oxygen is. So just by trying to transport it with normal piping, normal pumps, normal storage containers just won't work at all. On top of that, not only is it negative 270 degrees, it has to stay negative 270 degrees, because if it doesn't, it'll start boiling and turn into normal oxygen, which is usable. You can use normal oxygen to make the flame a lot bigger. It's just less efficient because liquid is much more dense, and the denser it is, the more you can store in a small space, the easier it is to move and all that jazz. So keeping it a liquid is very important. And that's also a huge problem when talking about small scale, because when scaling things up, or scaling things down, sorry, it doesn't actually get a lot smaller for a few vital components. For example, batteries that need to power everything that happens, like pumps and any sort of cooling or anything. That doesn't really get smaller, and it stays heavy. My plan was kind of to use a car battery to do all of this, and that would have been pretty heavy. So that was also kind of a problem. But more onto, well, after I encountered all those problems, I kind of decided, well, you know what, let's just like pretend that those problems don't exist. Let's just say, like, well, if I could theoretically somehow solve those problems and get all that, past all that, what would it look like? And I came up something similar to that. And I did a lot more research on things that probably weren't that important. For example, I spent probably a couple months researching pumps. And you would have no idea how unbelievably complicated those are. Holy cow. Specifically centrifugal pumps. They essentially work by spinning what's called an impeller, which is like a blade. Actually, it's this little doohickey right here. Well, that's the turbine. Wait, okay. Not that doohickey. It's what these blocks are representing, is the pumps. What I pointed out earlier, that like triangle thing, is a turbine, which I'll get into a little bit later. An impeller is shaped. So this is a top-down view of an impeller. and it spins around extraordinarily fast. And these are blades, and the fuel would get trapped in those as it's spinning around, and it turns the vertical or the linear motion into centripetal motion, which speeds it up really fast and shoots it out into a pipe that would be like around here, and then it would go out this way and then like wherever you want it to go. That's amazingly difficult to do, especially to make yourself, because I was also thinking about making that myself with 3D printing and such, just to have as a model. And there are a lot of ratios and awesome angles and cool science. Like, for example, the ratio between this right here relative to this angle right here, this angle, and this angle, which is basically the tangential line of this. So as the blade comes out, there's a specific ratio between this angle and this angle that you need to optimize in order to make it carry as much fluid as fast as possible. And that was a lot of research with a lot of derivatives that I didn't understand. And so I was like, wow, that's cool. Anyway, I guess I'll just buy one. So I looked at buying them. They're very, very, very expensive, like 10,000. Expensive because, well, normal ones aren't actually that expensive. They're like in the ranges of 300, but if you want it to be able, again, to handle liquid oxygen, it's a whole different story because it's such an extreme environment. Next up is like after it leaves the pump, where does it go from there? It's cool, now you're moving it, where does it need to go? There's a lot of places it needs to go, especially the liquid oxygen more than the RP1, because I've been hammering on about how awful it is that liquid oxygen is negative 270 degrees Fahrenheit. But it has one distinct advantage, and that whenever you're blowing things up, it gets really hot. Even if it starts off cold, it gets very, very difficult to prevent that metal. It's funny. The metal, like in the pipes, is freezing its butt off, and then the metal in that blast chamber that you're blowing everything up in is almost melting. So a solution to that problem is taking this very cold substance, and before you blow it up, you just make it do a few laps around everything that's really hot to cool everything off. So that's what this is down here. The liquid oxygen goes into this pump, and then it comes around this area and does like loop-de-loops around this nozzle, and then comes up and it cools off the nozzle so that it doesn't melt off and ruin everything. Then it comes back up into the blast chamber before it gets blown up, which is all cool and stuff. Metaphorically speaking, cool.
And so it doesn't get too hot while it's going around that. It's liquid and
It does. It can get really hot in there, but by that point, it's not too big of a deal because it's already all confined. So it's mostly a problem if it gets too hot in here, because then there's a lot of things going on. There's a lot of things going on in here too. Why you don't want it to get hot? Because if it gets, while you're pumping everything out of this storage container, there's going to be vacuums inside that storage container, and whenever, you know, because you can't just empty something and then have nothing take its place. And you can't just have air take its place, because that contains nitrogen, oxygen, all that stuff, which can react with liquid oxygen. So you have to replace it with an inert gas, which, you know, they have everywhere. That's actually a pretty common practice in like cars and stuff. So yeah, you're just filling it with gas. That's why you don't want it to vaporize or boil inside that storage container, because then it would mix with that gas and you wouldn't be able to pump it. But back to where I was. So it goes everywhere around the engine and the blast chamber to cool everything off. But on top of that, you're not gonna have battery forever. You know, that battery can run out. So to solve that problem, you generate your own electricity. And so before it goes through all of this to cool everything off, you siphon off just a little bit, which I forgot to draw the line for. Oh wait, no I didn't, it's right here. But for some clarity's sake, I'll redraw it. So after it comes out of the pump, it siphons off a little bit and goes to what's labeled right here as a GG, which is a gas generator. And that's basically a smaller blast chamber that you have right here. The only difference is that instead of shooting everything that's really hot out of the bottom to make you go up, it just keeps that energy and it shoots it back up into the system to this turbine, which spins an alternator, which spins the pumps, which spins everything, generates electricity, and everything like that. So not only is that is this reaction between RP1 and liquid oxygen generating the thrust needed to lift up this whole rocket, it's also doing a secondary reaction somewhere else in the rocket that creates electricity and kinetic energy, like the spinning of a turbine to generate power to power the rocket itself. It's like a self-fulfilling system. Once you start it, it can keep going until you run out of fuel because it's constantly generating more power to power itself. Of course, until you run out of fuel, which becomes a problem. After you send all that liquid, that reaction here, and you send it up through the turbine to power everything, you usually have a little left over, and after that, you can send the rest of it down here into the blast chamber to help you go up a little bit higher, which is cool. And then, what was I gonna say after that? Oh, another cool thing that I spent a lot of time looking up was single throttle, systems. Essentially, that is, you know, in your car, you can press down on the pedal, and the harder you press down, the faster you go. You can do that with a rocket. You can do that. However, if you do that, you can run into some problems because you're constantly going to be taking out the liquid oxygen from their tanks, and it's going to be essentially more complicated because the system that's stealing the liquid oxygen from the storage tank is going to be contained in a... Oh, shoot, how do I word this? Okay, how about I come back to that because I'll tell you the solution. The solution is you take it all at once, not all at once, all at the same speed, because if you do that, this is why. Okay, that's why, sorry. Having a pump operate at a throttle is dangerous because if you run it at too low of a speed, the centrifugal pump, which is what I was going on in this impeller, it's dangerous for the impeller because if you run it with not enough fuel entering into it, you can actually get like little cavities inside these blades, little vacuums of air that have nothing able to fill them because it's complicated derivatives. But when that happens, it can damage the pump. It's not good for the pump if you run it at really low speeds. So to solve that problem, you never run it at low speeds. You just constantly have it at a high speed, always pumping as much fuel as it can. And any fuel you don't need, you simply just take, after it's gone through the gas generator and all that jazz, you take it after that, and then you just put it back in. Any excess that you don't need gets cycled back into the storage tank, so that you're not always operating at max throttle. If you want to do like a small burn that's not as intense, you can just siphon off a little bit before it gets to the blast chamber, and that's how you control the throttle. It's kind of the opposite of what you do in a car. Instead of putting in more in order to go faster, you take away what you don't need, which is really cool. This project, although I haven't been able to build it, which is a little disheartening, it was very fun to research all this stuff. I have like a file with a whole bunch of PDFs of NASA documents talking about a whole bunch of stuff that I didn't think I would really be able to understand. And it's really cool. It's what I did in a lot of classes, Dr. Metter, you're included. Instead of doing work, I would just read NASA problems, NASA papers about this picture, which is cool.
You know, it kind of looks like a jet engine from, you know, from looking into.
That's actually a good thing because it's very similar. It is very similar. It's a different kind of. That's called an axial rather than centrifugal. An axial is different because instead of having the blades like this, you have them like this. They're kind of like fans,
Right.
and they'd be like this. And then behind it, you'd have another set of this, but off-kiltered and facing the other direction. It's different. I researched axial pumps because I was curious about them and if they would be better, but they're not. They're not better for this very specific situation. I did also, there's like hybrids. You can have both of them. And what that would do is that this one would start it, and then you would go into an axial pump, and what you'd have rows and rows of those like sets of blades, which would it would speed it up after it's already been through this. But those are cool. I don't know exactly why jets would prefer those. I don't know why that is the thing, but I know that centrifugal is better for me. That's about it. Other notes, I was planning on using a spark plug from a car to ignite this whole thing. I thought that was funny.
Would you have thrown the car battery into the ocean once you finished?
Probably. I mean, like, where else would I put it? Yeah.
I do have a question. So I understand that you're trying to build a rocket, but what is it exactly you're going to do with the rocket if, let's say, hypothetically, you do get it to work?
Well, my initial goal was 300,000 feet into the sky, which is out of the atmosphere.
And small payloads, right? Is
Yes.
that what you're?
That's the main like ideal or goal in this whole system was being like, would it be more efficient to send small payloads using a small rocket rather than using a big one, rather than sending big payloads with a big rocket? It's like, is the cost linear to send up payloads depending on the size and of the rocket?
But the oxygen was the issue, is that what you're saying? Or
I'm sorry?
the liquid oxygen was the issue, or one of the?
Mostly, it was mostly the issue.
Because of, yeah.
It just doing anything with liquid oxygen becomes exponentially more expensive.
So what's the difference between your rocket and, let's say, NASA's rocket, like small?
Very little, actually, very little. They're practically the same, except this is just smaller.
So what makes yours more efficient?
Well, that's the theory I was testing. I don't know, actually, if it makes it
okay,
more
that makes
efficient.
sense. So this is just all hypothetical.
And if it's not, worst case scenario, I built a cool rocket. which was cool.
And how do you turn it? If I remember correctly, you said you can turn it off and on.
Yeah, that's one of the advantages. You can literally just do that by stop feeding it fuel.
And where is that located on the diagram?
Well, that would just be the pumps. Like you
Oh,
just
just
turn them
pumps.
off.
Oh,
Like,
just okay.
yeah,
makes
if you just stop it, you could just turn them off and then turn it back on whenever you need to. You would need to have a starter, which is actually, I say that you can turn it off and on,
Mhm.
but in order to do that, you actually need some extra parts in order to do that, because remember when I said that the pumps and all this is fueled by this gas generator? You have to like kickstart that gas generator, which essentially means you have to have a little bit of fuel in there in order to get the gas generator started to power the pumps and power the whole thing. I don't have the parts that could resupply that gas generator, kind of. So once you turn it off, it would be dead.
Makes sense.
You know, I would have to like basically prime it before takeoff, and once it starts, it'll keep going. I decided to forego that because it would be more complicated, more weight, which is a big deal.
Mhm.
Any other questions? Or anything? Am I looking good on time? Do I need to make up some stuff to make it last longer to get a good grade?
You're 25 minutes in.
No, I think just if anyone has questions, we can do that.
Mhm.
Jason's asked a few already. I know Camden has about 3 he wants to ask.
No, I don't. I don't know anything about
So-
this.
I can't even count that high, so.
Okay, so I noticed you drew like one thruster. I'm assuming you're gonna have 3 more, is that correct? With this rock? Or is it
You're
just?
talking about this?
Yeah, that. Is there going to be 3 more, or is it just going to be 1?
Why would there be 3?
I don't know, because I was thinking like, when I see a rock, I see like, there's 4 thrusters total. But this one I see there's only 1.
No, you don't need 3 more. You can have as many as you want. Why I would think they would do that is because it's probably safer to have 4 small explosions going on than 1 massive one.
Oh,
That's probably a safety thing.
so yours is more like the massive one instead of the 4 medium ones going on.
Yeah, but I doubt it would be a problem since it's already such a small scale.
Right, because there's not that much weight for it to go. That makes sense.
Yeah. I mean, as cool as all this is, I always knew in the back of my mind it wouldn't be as cool. Like, there are so many little things that the massive rockets have. Like, for example, gimbaling. That's cool. It's basically when you angle that thruster at the bottom to like go different directions to basically steer.
Yeah, directly.
That would be hard. Decoupling, which is basically staging, that would be difficult, especially because if I wanted to have it go higher than what one engine can provide, you basically stage it, make another engine, and then keep going. But that's also probably pretty difficult. There's like just a lot of stuff, small stuff. But getting the engine all theorized was enough for me, honestly.
So let's say if this is just a if case scenario, because this is what I was kind of thinking in my head. Like, let's say if there's a strong headwind coming directly at the rocket, how would you be able to produce enough thrust to go like above from that, like to counteract that?
Probably wouldn't launch. I'd probably just wait till it wasn't a windy day.
Right, but I'm saying, assuming if it so happens to be windy,
You could,
because these are kind of like the questions you have to ask. You know,
Yeah.
if it does happen, you're like, oh,
I mean,
now it's happening.
I can always, I'd obviously wait for an optimal day. I'd obviously wait for like the most optimal day to launch it. But if that were to happen, I'm pretty sure it's not the worst thing in the world. It's pretty bad because I would get off course. But because it's going so fast, the wind isn't enough to like make it flip over, unless it's going like really fast, probably. I don't know. I didn't do too much research into that specific department. But since I don't really have a destination anyways, I would just want to go up as high as I can. The specific course probably doesn't matter too much.
Wait, but you said you want to get up to
300,000 feet.
300,000
Up.
to send a small payload.
Yeah.
So there must be some kind of direction you're kind of sending out to. That's what I'm assuming, right?
Well, it's mostly just whether or not it can get that high. And then if I wanted to work for NASA, my goal would be whether or not it can rendezvous with a craft in orbit. Because there's no point in sending a small payload up 300,000 feet up if it's not going to stay there or do anything or help anyone.
I mean, yeah.
So in that case, I would definitely care about the wind, because then I'd have to, figure out how to counteract that. And it's, that's way later. Yes?
You had originally talked about actually what was gonna be the rocket body in different materials, and you were talking about steel or something like that.
Oh, yeah.
What all were you thinking about? Because you had a lot of ideas for that.
I believe I settled on stainless steel, 304 stainless steel. That's because it has the
But
high.
it's heavy, right? Or is it not?
It's of the stainless steels, I believe it's the lightest in this class. It's what the Starship is made out of. And yes, it is heavier than a lot of other things, a lot of other metals. For the actual body on the outside, like the main shaft would be polyaluminum because that's I settled
Light.
well, yeah, it's very light, and that's a lot less extreme, you know, environment, although it does get really cold up there, but aluminum would be fine. For the inner workings, like the blast chamber and such, yeah, stainless steel would probably be pretty cool. Just because it has a very, very high critical temperature. It has to get really hot in order for it to like start bending or cracking or doing anything like that.
Well, man, I wish you had a rocket that we could see.
I
but,
wish
you
I
know,
did too.
I appreciate you talking about it. Any other questions for anybody?
Cool.
All right, thank you, Casey.
Cool.
Appreciate it.